We have been speaking about binary trees. We looked at the notion of perfect trees, then we went on to look at complete trees, and then we saw how we can impose this structure onto a list. The way we did this was this notion of top to bottom, left to right, and that made sure that the trees that we impose onto these lists are always complete trees. And when we first discussed it, I just said that, okay, there is a reason we are doing this. There's a certain, let's say, properties that come out of this. We are at a time now to start discussing those properties. So we are in this video going to look at some very important properties, that of how this structure is creating the relationship between the parent index and the child index. Let's start with perfect trees. Remember, perfect trees are those where all the levels are completely occupied. Clearly, approximately 50% of nodes do not have children because they are the leaf nodes, right? So for example, if you look at this, well, nearly 50%, so 8 nodes do not have any children, and these are the leaf nodes. Remember that these are those nodes which are in fact also residing at the very end of the list, because we have filled the list of top to bottom, left to right. So these nodes after a certain index, in fact, these are the leaf nodes. A non-leaf node which is at index I has children at 2i plus 1 and 2i plus 2. So what do I mean by this? Basically, remember, every node in a perfect tree has two children. The index of the left child is 2i plus 1. Index of the right child is 2i plus 2. Once again, examples will clarify this. So let's think about it. We have root node here 12. Its children are 24 and 11. Remember, the indices of this index I was 0 over here. So children of this root node are at index 1 and index 2. That's 24 and 11. Let's go further. Look at this node over here. So I've kind of put in a square as well. This node over here, whose value is 24, index is 1 because the list index is 1 over here. The children are at 2i plus 1, that is 3, 2i plus 2, which is 4. So children are 13 and 18, which are at these two locations. Similarly, let's look at this node here. Just as an example, you can look at any one. In fact, just as an example, if you look at this node here is item 6. So 0, 1, 2, 3, 4, 5, 6. I've marked the index in this, let's say, the magenta color. This node's value is 2. Node is 6. So we are saying that, look, its children are 2i plus 1, which is 13, and 2i plus 2. So left child always 2i plus 1, right child at 2i plus 2. The children's values are 8 and 19. The indices are 13 and 14. So this is a parent. The two children are here and here in the list. Remember, the tree structure has been imposed onto this list, but the way of imposition has caused this rule to come up that, look, the children are, for a node which is at I, its children are at 2i plus 1 and 2i plus 2. Clearly, leaf nodes do not have children, so which means I is bounded by, let's say, in this case, 0. The converse of this, for a given node at node I, the index of the parent is given by I minus 1 floor division 2. Now, the best way to understand this is look at examples. Let's look at, for example, this tree that we had, these two children. This is 3. The parent was located at 1, and that's because 3 minus 1, which is 2, floor division 2 is 1. If I looked at this child, parent is also located at 1 because 4 minus 1, which is 3, floor division 2 is also 1. So basically, for children index I, the parent index is given by I minus 1 floor division 2. For a parent index I, the children indices are given by 2i plus 1 and 2i plus 2. You can in fact apply this to any any node, and you'll see that this result is coming out. Let's look at one more example. Node 13, node 14, exactly what we have done. Once again, the children for this, the parent for this two children are at 6, because remember also that every child has only one parent here in the tree. So basically here, look, 13, 14, this is 6. So we can apply one more place. Maybe look at this node. Node index is 5. The children have to be then at 2i plus 1, 11, 2i plus 2, 12. If I see from the child point of view, to locate the parent, I have to go child's index minus 1, floor division 2. That is indeed 5. 10 minus 1, so 11 minus 1 is 10. Floor division 2 makes it 5, right? So this, the way we have filled up this list the way we have sort of imposed a complete tree onto this list is giving rise to this very interesting property that, look, children are 2i plus 1, 2i minus 2. And given a child, the parent is I minus 1 floor division 2. This becomes very important later on as we start programming. But then you may ask, okay, what happens if this is, let's say, not a perfect tree? So for example, let's say, I had a list which had only 12 items, right? So I'm not going to end up with a perfect tree over there. But the beauty is that the same relationship holds for trees that are not perfect. The only catch being that some nodes previously which had children now may not have children. But the way to see it is that, let's say, if these nodes were to have children, this is where those children would have ended up. Again, example will make it very, very clear. So for example, let's look at node number 5 over here. So there's only 12 items, so that's why it's 0 until 11. Remember, we filled from left to right. Node number 5 here, remember, children were at, we're going to be 2i plus 1, 2i plus 2, so that's 11 and 12. Obviously there's nothing at 12, so it has only one child, but this one child is at 11. If there was a second child, the next item would have definitely ended up here. That would have been child of this node, and that would have been at 12. Let's look at the last node. Remember, by the rule of, let's say, by the rule of, let's say, complete trees, the children have to be at 13, at 14. Had they absolutely would have been there if we had children, but now that we don't have children, that's okay. This is empty, right? So basically the rule is still holding, just that some nodes do not have children. So the way to look at it is that, for example, let's say for node 5, if the right child was present, it would have been at index 12. If for the node 6, if these, let's say, left and right children were present, they would have been at 13 and 14. And remember, because of the top to bottom, left to right rule, it is not possible to have children for node 6 before this is completely filled, because we are filling from left to right. So we'll always have a complete tree. We cannot have, let's say, this being filled up. So think through it. Very, very nice, very, very powerful. And this forms the basis of heaps, right? So we have learned how to impose a complete tree onto the list. Now that is giving us this rule that if the parent node is at index I, its children are at 2i plus 1 and 2i plus 2. Conversely, if the child node is at I, its parent is given by I minus 1 floor division 2, right? So we looked at several examples. This rule is central to the whole definition of heaps. So kind of internalize it, convince yourself that these rules are working, considering that we are looking at complete trees. Happy to discuss. I hope you found this interesting. Do look at our website www.ybyte.in for more such content, and forever enjoy coding. Take care. Thank you so much. Bye bye.